Welcome back to this lecture on set operations. In its sixth and last segment, we're going back to the theorem that we proved in the previous segment, but we're going to provide two different proofs of this same theorem. Now remember, in the previous segment, we proved this theorem by mutual containment. That is an important proof technique you must be familiar with, but in this segment, I want to go back to an earlier proof technique that you should already know called proof by equational reasoning. Remember, the way this proof technique works is if you're trying to prove that two objects are equal, you could start with either one of them, say this one, and you can rewrite it in successive steps until you end up with the second half of the equality, and you just prove that the first one is equal to the second one, as long as at every step you're using well-known and valid equalities. So let's apply this proof technique to this theorem. And let's start from the left-hand side. The complement of R intersect S. Well, by definition, or rather using the set builder notation, this set is equal to all the values of X such that X belongs to the set we're interested in. So this step does not tell us anything new. This is just another way of writing the same set. The advantage of this first equational reasoning step is to replace this set by this set, is that this notation here now can be unpacked and transformed into a definition for this set. So let's do that. What does it mean for X to belong to the complement of R intersect S? Well, that just means that X does not belong to R intersect S. Now, this symbol here is really a shorthand for a negation statement. So let's write it down in logic. It says it is not the case that X belongs to R intersect S. Now let's use the definition of intersection to replace this part of the set definition. What does it mean for X to belong to R intersect S? Well, it simply means that X belongs to R and at the same time X belongs to S. And now this is the crux of the proof. We have a negation of a conjunction, and therefore we can replace that with a disjunction of negations. Namely, it is not the case that X belongs to R, or it is not the case that X belongs to S. Notice the justification for this step is what? It's one of De Morgan's laws for logic. And what you should realize here is we're already trying to prove one of De Morgan's identities, but that's not the same one. Here we're talking about De Morgan's identity in set theory. Here we're using one of De Morgan's laws in logic. And that's the crux of the proof. It's not begging the question. We're not using this set theory equality to prove or to infer this proposition. So this reasoning is completely valid, and that is the crux of the proof. And now it's basically down here to rewrite this proposition here as a series of steps until we reach the definition of this set. So, if it's not the case that X belongs to R, it must be the case that X does not belong to R, and similarly for the second disjunct here. Now, if X does not belong to R, by definition of the complement, it means that X must belong to the complement of R, and similarly for the second disjunct here. Now, by definition of union, if X belongs to this set, or X belongs to that set, then it must belong to the union of the two sets. So X belongs to R complement, union S complement, and this set builder notation is nothing but the definition of this set here on the right hand side. So the last step allows us to conclude the proof by equational reasoning. So, in a previous segment, we proved this theorem by mutual containment. Please make sure to remember and be comfortable with that proof technique because you will use it later. For example, if you take Computer Science 381, that's going to be a crucial proof technique for you, and we might even use it later in this course as well. So, proof by mutual containment is one way to prove that two sets are equal. Another way, as we just illustrated, is proof by equational reasoning. And finally, remember that a third way is to use membership tables. So I will let you write this third proof of the same theorem at home. Shouldn't take you too long. There are only two sets involved in this equality, so that should tell you how big or how small the membership table will be. Just remember the similarity between the membership table and the truth tables. Now, it doesn't mean exactly the same, obviously. In one case, 0 and 1 means that the element doesn't belong to the set, or it does. In a truth table, 0 and 1 means false and true. But I hope you remember the similarity between the membership table and the truth table. In any case, this concludes our lecture on set operations.